This is a follow-up addendum to a collimation suggestion I proposed earlier to the 30-meter telescope design team on YouTube. I also want to be clear to note that this study is not a product from that program. These are all my suggestions. My intent here is to identify another laser collimation methodology. This slide is a summary of that original proposal. It demonstrates that a laser beam can be set up in a telescope to a designed optical axis, and then that the primary mirror can be aligned to that beam. The problem is solved was that Cassegrainian optics are usually perforated, and a necessary reference surface required for laser collimation is missing. This methodology uses what I call a virtual pinhole. In this test, an on-axis laser beam is set up to strike a 3am type reflecting film near the mirror's center of curvature, creating the virtual pinhole. That reflecting film then returns a concentration of light, but it will be sufficiently scattered to pass around the secondary mirror and fall on the primary. There will be enough light to create an image on the film near the original laser strike. For collimation then, all that is necessary is to adjust the primary mirror until the two images become coincident. These views show the adaptation of that methodology for the TMT, shown first at 1 in the original proposal, and in the added methodology of this presentation at 2. For method 1, the mirror segment's cell is shown as foundation structure, and the mirror segment is a standoff element with collimating and adaptive optic elements in between. The laser for that segment is shown buried within the foundation cell structure, and a clear path is created through the mirror along its optical axis. For method 2, a dedicated laser is fixed directly to the mirror disk along its optical axis. The difference from 1 is that instead of having a perforated path for the beam to pass through the membrane structure, that is the shear plate, the laser assembly becomes part of the mirror disk, permanently aligned to its optical axis. Should this prove to be too difficult or complex, it may be offset through the disk, option B, but its target on screen must always be on the array axis. This is a summary of previous information. The key element of method 1 is that it is possible to predefine an optical axis with a laser beam, and by the use of a virtual pinhole, be able to bring that mirror segment into alignment with that beam. Method 2 is more of a hardware issue, placing a lot of critical items in a prime location and demanding a constant relationship to the mirror disk. Method 1 will be easier to align using more accessible Hartmann-like targets to position the beam. See the original presentation. Method 2 lends itself to alignment and testing of radii zones along the optical axis and is strongly related to spherical aberration metrics. These figures go into more detail on the hardware supporting the added method 2 concept. Method 1 is referenced above right, and for that a link is provided to the original YouTube presentation. The graphic, upper left, shows a laser device hard-mounted to the mirror disk and physically passing through the structural membrane to where the disk is attached. The laser is clear and isolated from that membrane to avoid flexure problems. Such a device may be aligned as shown in the figure below, with the mirror segment uniformly supported in a balanced horizontal position and reflecting off an optical flat to the retroreflective film for alignment of the beam. If the laser penetrates the mirror somewhere else off axis, then it must be sure to cross or intersect the optical axis at its center of curvature, Rn. As method 2 involves primarily laser beams and their paths, a smaller optical flat may be sufficient to achieve that alignment. This slide clarifies how the varying centers of curvature by zone radii, small r, are sequenced and lengthened for each mirror segment as a function of its radii, small r, as it increases. Because the mirror array is comprised of 6 identical sectors, sector A is shown here, there will always be at least 6 and sometimes 12 mirror segments that have identical radii and therefore comprise a set or a group. At any given radii center of curvature when illuminated, all 6 or 12 segments of that radii could be simultaneously illuminated. Sector A, upper left, shows numbers representing that segment sequence from the shortest R1A to the longest R49 radii. When a number repeats and has a subset number of 2, that indicates that another segment exists within that same sector that has the same radii and therefore is in the same array group. Note that these segment numbers are not the same as mirror segment numbers assigned in TMT documents. The lower figure to its right shows 6 or 12 segment ring or set examples dispersed within the array. Note that all segments belong to either 6 or 12 segment groups. A significant feature to note is that all image sets converge to the same on-axis center of curvature point. The best way to assess these segments, therefore, may be by linear scanning them along that Z array axis, 1 by set group and CC center of curvature radii, and 2 within each set group sequentially and individually in their metrics for pass and veil. And in continuation of that same assessment of pass-fail for method 2 lasers, the only thing we were doing is assessing the alignments of laser beams representing that segment's optical axis to the extent that they are themselves accurate. From the main figure left, diametrically opposed lasers should come together and cross the array axis as they pass through their centers of curvature, just like rangefinders, except there is little value in this as ranges are predictable from formula. The above drawings reflect what has just been stated. What could be helpful if incorporated would be an array centerline laser shown in green, which, if all images were shown sequentially and illuminated in order, could be developed into a protocol reference for assessment of pass-fail. In a similar manner, a combination of all images with the histogram of image density and distribution may offer a faster assessment. In more detail, the first group of figures shows how range-finding visuals can help verify a center of curvature, working with diametrically opposed sets of segments, using 3 or 6 sets from a standard 6 or 12 group may be the best way to quantify that group for certifying the array. Analysis of a whole set may be easier if done in blink comparator fashion. Another green or distinctive laser may be preceded sequenced individual beams to assess them for pass-fail. At the end of the sequence is shown a composite overlap of the set, showing why it may be too difficult to see at once unless done automatically, where distribution can be integrated to an effective minimum. What is being measured is the beam energy distributions, but there is another factor to consider. While we are thinking of these beams as circles on the screen or detector, the fact that these are at the mirror's segment's center of curvature, that mirror, and in fact all mirrors in that same set, will be seeing the same light and will return images of that light back onto itself, as shown in the third image. It will not be as bright, and there will be an unpredictable distribution or scatter of those images behind. The second set of blink comparison is repeated to include this combined imagery effect. The best approach most likely will be to automate the finding of the real laser images sequentially by turning on and off each segment laser at the predictable time keyed to its proper position relative to the detector screen along its z-axis scan. The objective of this slide is to show that measurable zones on the array z-axis in the order of about 2 meters, a little bit less in length, along which the crossover properties of the laser beams show their effects as they pass through their centers of curvature. Ideally, an axial scanning device will be used for method 2 evaluation along the z-axis between R1 and R49. The intent of this slide is to show other laser location options. The on-axis position A is far superior to all others in that it eliminates parallax errors that may result from image screen distance variations. A feature of both methods 1 and 2 procedures is that they will be insensitive to position errors of the screen. This will no longer be the case for B, C, D, or E placements of the laser. Optical windows have been assumed in lieu of simple holes through the mirror segments for maintenance and housekeeping reasons. In a case for the E variation, a hex segment corner may be clipped off as the edge is already exposed. Drainage and leakage concerns would not be an issue. Range finding with BC sets is not all that valuable. Adding D4 representation of ordinates by XX and YY imaging may be easier or faster to assimilate. However, the cost of redundant lasers may not be worth it. Design of a Z-axis sensor detector should include for its range the nearest center of curvature, R1, created by its mirror segment, increase over its base, R0, by an amount determined as a function of its offset distance, R1. The sensor detector should then be able to translate further to accommodate the longer R26, a mid-zone segment among many, defined by its small r26 segment offset. Segments may be assessed using diametrically opposed sets, this one comprised of 12. And lastly, the furthest and longest R49 shows the full extent of scan stroke required to accommodate the procedure. Also note, however, that this scan perhaps should be done first. The reason for this is that these R49 diametrically opposed lasers offer the widest base and most accurate range finding potential for finding the center of curvature for that zone, as well as having the greatest impact on effect, also representing the greatest mirror segment area. From this accurate determination, the position of R0 can more precisely be defined, and from which all aberration corrections defining the other zones are ruled. The scan protocol should be developed around this datum using the R49 metric as a starting point and working backwards. This is a first cut at applying the preceding to general TMT dimensions. The folded path feature is the most significant element of what is proposed, as it rids the problem of mechanizing a scanning device which is treacherously supported and is in its own way of the problem. It at once is able to scan from the other side of what is being scanned, but also places the hardware in a substantial, stable, sheltered position. As laser beams are what are being assessed, it is felt that sufficient auxiliary lasers are available to establish datum references to correct any distortions resulting from mirror flexures. Unlike Method 1 methodologies, there are no mirror wavefronts being overlapped or doubled up to expose collimation problems. When combined with the ability of selectively placing segments in zenith positions, azimuth controls and telescope and dome systems can selectively map out the entire array with smaller mirrors. Shown here are mirrors for servicing mirror segments in meridian-like zones, rotating either for polar-like coordinates for full coverage. The most critical problem will be that diametrically opposed scanning will require coordination between opposite sector scanners for comparison. This second architectural resolution may allow a whole array single image solution. If a large enough circular reflecting mirror can be effectively deployed. Alternately, a single precise long narrow plexiglass mirror vacuum chucked to a composite sandwich may be able to provide a meridian-like rangefinder view to capture the widest full array opposed opposites mirror segments. Note that this imposes a significant change that impacts the existing TMT shutter architecture.